Good morning, everybody. Many of you know I've been very excited about this presentation for several weeks now. I believe that climate change is one of the most important issues we cover in our environmental science class here at UMBC. It's truly an honor for our geography department to welcome Dr. Forrest Hall this morning. Dr. Hall, a physicist, is currently a professor of physics right here at UMBC, and he has been an adjunct professor at John Hopkins University, where he's taught in the Planetary and Earth Science Department, the Hopkins MLA Department, and in its Odyssey programs. He collaborates with a number of scientists at NASA's Goddard Space Flight Center. Dr. Hall has been active since 1980 in global change research using Earth-observing satellites and models to monitor human-induced and natural changes to the Earth's land ecosystems and the effects that those changes have had on the Earth's climate. He has authored more than 80 scientific papers in quantum physics and space science, and more recently on satellite monitoring of the global carbon cycle and climate change. Many of those papers have been highly cited. For this work, he has won many awards, including the 2009 William T. Pecora Award, presented to individuals or groups that have made outstanding contributions toward understanding the Earth. Dr. Hall is a regular lecturer, both nationally and internationally, and has addressed a broad range of audiences on climate science. Dr. Hall has a BS in Mechanical Engineering from the University of Texas and an MS and PhD in Physics from the University of Houston. It is with great pleasure that I ask you to join me in welcoming this morning Dr. Forrest Hall.
Wow. So if you've been around as long as I have, it's easy to accumulate a rich CV. And so I hope all of you will spend your life, or at least most of your life, as I have, in studying climate change and trying to understand the underlying causes of climate change, in a sense, trying to predict the future, trying to understand what it is we can do about the climate to mitigate its changes, the rapidity of its changes. And for some of you, maybe, being engaged in the political process, which may be the most important thing of all to affect the kind of mitigation measures that we need to make to reverse our climate change. So I'm going to be shamelessly plagiarizing from materials including from the National Geographic magazine recently, published an entire issue called Cool It. So I'm going to steal some of their imagery. And their thesis is climate change is here. Record heat, melting ice, and rising seas show how climate change is affecting us. The second line says, but there's new hope. And where do you think that new hope may lie? We have the means to reverse the damage that we've done. There's the new hope, and also the new hope lies in trying to encourage decision makers and policy makers in this country to begin to accelerate the implementation of the kinds of technology that are needed, and also the conservation measures that are needed to begin to reverse the rapidity with which our climate is changing. So I want to talk about those issues. I want to talk about how our climate is changing. I want to talk about what we can do to begin to mitigate the impacts that we as humans have on climate. We're the people causing the climate change. It's not the elephants. It's not the bluebirds. It's us in this room that are engaging in our culture in such a way that we are actually affecting climate. So that's the good news, is it's us. And the reason that's the good news, that means that we can do something about it. It's not some natural force out in the heavens somewhere, the sun or Mercury or Venus, that's causing climate change. It's us. And as I say, that's the good news. Okay. So, just in case that some of you might disagree that we have climate change, a major problem on our hands, I just remind you, if you haven't been reading the newspapers, of what we've seen since 2012 through the present. So the largest global disasters of 2012 were Hurricane Sandy. If any of you lived in New Jersey, you certainly will remember Hurricane Sandy. Cost $65 billion in damage. And the year-long Midwest Plains drought cost $35 billion. Global disasters in 2012 combined to cause economic losses of around $200 billion, which is just above the 10-year average before that of $187 billion. So we see the impact and the cost of climate change increasing. Into 2013, we saw floods in Colorado. We saw floods in India, Budapest, tornadoes in Oklahoma, fires in California. Last year, if you remember, or year before last in 2014, drought seemed to be the plague that was affecting most of the area west of the Mississippi. And of course, just yesterday, if you watched the news, we saw that trend reversed in Houston and Dallas, dropping 18 to 20 inches of rain on those cities in less than 24 hours. And because we've built up the environment with impervious surfaces, when you get that much rain, you get a lot of flooding to go with it, a lot of displacement, and a lot of economic damage. So what we're worried about here, and I want to impress this on you, I'm not going to be forecasting the end of the earth today, but I am going to be telling us about some of the economic and other dislocations that climate change can bring on us. We've all grown up in a certain climate. Perhaps it wasn't our favorite climate, perhaps it was. But whatever climate we have grown up in your lifetime, it will change significantly. So, might be a good job to look around some of the climate forecasts, decide what kind of climate you like, and think about making that your new location, because climate will be changing no matter where you are. Already is. You remember last year in 2015, the big deal was El Nino. We had this pool of warm water that migrates, not periodically, but quasi-periodically from Indonesia, migrates across the Central Pacific, parks itself off the coast of Peru. So we have this big giant pool of water that's 8 degrees centigrade, 14 degrees Fahrenheit warmer than usual. That stuff starts moving. It parks itself off the coast of Peru. And of course, when you have a patch of water that warm, it creates lots of havoc including flooding, and I mean global impacts. Some have suggested replacing the term global warming with global weirding, because the climate is indeed getting so much different, weirder if you will. Okay, so climate is changing. That's kind of a pictorial tour. I'm going to give you some numbers later. And I'm going to give you those numbers based on the research that NASA started doing in the early 1970s. This is when I stopped being a space scientist and switched my job, my role, to becoming an earth scientist, an earth physicist, if you will. Around 1970, NASA discovered that the Earth was a planet, and we decided to launch a number of satellite observatories, which are still up there now, even as we speak, monitoring the Earth's atmosphere, monitoring the Earth's oceans, monitoring the Earth's terrestrial surface, monitoring the Earth's cryosphere, its frozen part of the planet. And we are also now beginning to look at the impact on food globally. Populations are increasing. As climate changes, the seasons change. The variability from one year to the next changes. The timing of the seasons, I should say. When and where the precipitation occurs changes. And as this becomes more variable, this has an impact on crops, because crops are grown in particular regions of the world now tuned to the particular climate. So we grow winter wheat and spring wheat in the U.S. Central Plains. We grow corn in Iowa and Indiana. We grow a lot of avocados and almonds in California. Well, all of these regions are being affected by climate change, either getting wetter or drier, or the season shifting, and that's having an impact on food production, especially in other countries. And as climate variability increases, it's not just the secular trend in climate, it's the climate variability. As that increases, that's making it increasingly more difficult to adapt and maintain the food supply. Because food is not a problem until you have a year in which a big change in climate creates shortages in food. It can be low temperatures, drought, high humidity leading to fungus and diseases and so forth. In those years when you're a country, a nation with marginal food supplies, those are the years where you can experience mass starvation. So those are some of the evidence that the climate is changing, and that's some of the impacts that we have to worry about. So let's talk a bit about the physics. Savante Irenaeus in 1889, in his book Worlds in the Making, first describes the hothouse theory of the atmosphere. As a chemist, he discovers that carbon dioxide is a greenhouse gas. What that means is it lets light through the atmosphere, but it traps heat, and we'll be talking more about that. Here, as a matter of fact. So, a number of greenhouse gases, water vapor, methane, carbon dioxide, they're perfectly transparent. This room is full of water vapor, it's full of carbon dioxide, probably even a little of methane, but it's transparent to visible light. But it is not transparent to thermal radiation, that is heat energy. And so the surface of the Earth, the oceans, the lands, the ice are heated as sunlight passes through the transparent atmosphere, but then once it warms the oceans and the land, it traps heat. So greenhouse gases are good. If it weren't for the greenhouse gases in the atmosphere, our average temperature on the Earth would be probably very unpleasant, probably too unpleasant for much of life, and so probably about 30 degrees colder on average than it is now. Well, since his observation in 1889, 70 years passed without much notice of his observations until in 1958 a scientist at the Scripps Institute in San Diego, Charles Keeling, decided to take on as a dissertation topic, he was a chemist, the challenge of measuring atmospheric carbon dioxide concentrations. So wisely, he picked the location for his study in Hawaii, where I was this summer to buy this Hawaiian shirt. So he spent his time very near where I took my vacation, Mauna Loa Observatory. He took some flasks up to the top, captured atmosphere in a bottle, brought it back to his laboratory in San Diego, and within 3 years, he discovered something amazing. He discovered that the carbon dioxide content in the atmosphere in the 3 years of his studies had increased dramatically in the atmosphere. So what's going on there? He and Roger Revelle, his mentor, were the first to alert the world of the possibility of anthropogenic contributions, meaning contributions to the atmosphere from the combustion of fossil fuel. So, as time continued, then we have had a steady presence at Mauna Loa. So here were the 3 years of Keeling's graduate school studies. And so we see that since his time, atmospheric concentrations have increased from about 315 parts per million to 390 parts per million. And this is as of 2010, it's now more than 400 parts per million. Well, parts per million, that doesn't sound like a lot, but it turns out that the Earth's climate is exquisitely sensitive to the level concentrations of greenhouse gases in the atmosphere. It doesn't take much to tweak the climate of the Earth. And this has been more than enough to actually raise the average temperature of the Earth about 0.8 of a degree centigrade, about 1.5 degrees Fahrenheit. And it hasn't done so evenly across the globe. It's raised the temperatures more at the high latitudes. In the Arctic, we're beginning to see the impacts early in the case of thawing ice. What's beautiful about this curve, in addition to it being a little scary, what's beautiful about it is you see the annual cycle. The Earth breathes. The Earth is really, at a global scale, a living system. So it exhales in the middle of the year as plants are dormant, photosynthesis is minimum. Plants are undergoing respiration. As we undergo respiration, they're exhaling carbon dioxide. But then in the springtime, just about now, as the northern hemisphere, remember most of the vegetation is located in the northern hemisphere, as the photosynthesis begins from the seasonal cycle of the Earth, the Earth's biosphere begins to inhale once again. And so we see this beautiful rhythm of breathing of the Earth, but it's getting increasingly more rapid and causing a number of issues. So it's easier to understand the impact we're having when we look at this paleo record, climate record that's gathered from drilling ice cores into the into the Antarctic, taking the ice cores, analyzing year by year by year the carbon dioxide concentration in the ice cores, and inferring the temperature of the Earth, average temperature of the Earth, from looking at oxygen isotopes included in the cores. And what we see here is the peak of the last glacial maximum 20,000 years ago, when Chicago was buried under about a mile of ice. And then slowly we begin to see the warming trend. This is the blue line is the warming trend. The red line is the carbon dioxide concentration measured in the ice cores. And what we can see is over the last 10,000 years, we've had a beautiful, perfectly acceptable climate for human to develop, for cultures to develop, for civilizations to develop. So we have made the transition from the hunter-gatherer that we were, moving from one spot to another, in this period being chased by rising sea levels. This is a plot of the sea levels, how they've risen almost 14 meters in this time. So until finally we reached a period called the Holocene. The Holocene sea level has been relatively constant. The climate has been relatively constant. And what this red line shows you is where the carbon dioxide concentration in the atmosphere has gone in just the last 100 or so years in the post-industrial revolution. We started burning coal to fuel our industries, to fuel our air conditioning. Seems rather cold in here. Maybe we're using too much air conditioning. I don't know. Might want to ask the administration to tone it down here a bit. Any rate, we're above 400 parts per million in the atmosphere right now. And so when you look at this scale, it's much more alarming. When a physicist sees this, he sees a climate signal that's periodic, quasi-periodic, like a bell, almost like a bell ringing. And you know, when you hit a bell really hard and you hit it too hard with a hammer, it may be that the bell not only rings louder, it may be like the Liberty Bell. You crack the bell. That's not what happened to the Liberty Bell, incidentally. But you can see that we're concerned about climate tipping points. We don't know how hard we can drive the climate before it begins to tip. So you see here this rapid rise in carbon dioxide concentrations since Keeling. This is Keeling young, Keeling older, and now his son has taken over for him. He's passed on. And to get a feeling for it, though, the average solar energy, average over the Earth for a year, absorbs about 240 watts per meter squared. So a watt's about the amount of energy that a Christmas tree light bulb puts out. The old bulbs, not the new ones. The new ones are much more efficient. 240 watts per meter squared. And there was a change in the budget during the interglacial. This is what the Earth looked like 20,000 years ago, last glacial maximum. This is what it looks like today. And in this period, we saw a change in only 3 to 5/10 watts per meter squared in the total energy budget of the Earth. So this is of great concern to see the kind of sensitivity the Earth's climate has to slight variations in the greenhouse gas. Well, over the past 10,000 years, the Earth has been, well, actually over the past 700,000 years, but especially over the past 20,000 years, 10,000 years, the Earth has maintained a quasi-equilibrium. In other words, it somehow knows how to regulate its climate. Evolution has been such. In fact, through the entire Earth's history, from the formation, the origin of life 3.5 billion years ago, life has managed to regulate the climate of the planet so that water is always above freezing somewhere and it never boils away anywhere. And so life itself has been regulating climate to be suitable for itself by the amount of water vapor, carbon dioxide, and methane that it has maintained in the atmosphere. And of course, along we come, the last industrial revolution, and we're injecting a huge amount of fossil carbon that's been buried for hundreds of millions of years. Fossil coal, the largest source of energy right now for the generation of electricity worldwide, as well as the largest worldwide anthropogenic sources of carbon dioxide. So this is why there's a big push on the part of this administration currently to reduce our dependence on coal. Also, the good news is there's a big push in China to reduce their dependence on coal. It's interesting to think that they may build 150 nuclear power plants over the next decade or so. So they're trying to get away from their... So the question is often raised by, not scientists, by the way, by people who are not scientists, are humans really responsible for climate change? And I think the answer is pretty clear. That's the good news. We are responsible. Over the past few million years, as I've said, as we've evolved from anthropoids to Homo sapiens to hunter-gatherers, as the climate moderated around 10,000 years ago, we've settled into the communities and we domesticated both animals and plants. We became farmers. But then came the Industrial Revolution. And the Anthropocene is a period that has been a kind of semi-adopted as a new period of climate following the Holocene. And that term is widely popularized by the Nobel Prize-winning atmospheric chemist Paul Crutzen. So, if we look at global population, fairly stable until about 1950 or so. Sorry, you can't see this axis. But since then, we've had a very rapid rise in the global population. Here we are somewhere, we are beginning to see a little bit of a turn down as global birth rates have dropped, and so we're hoping that as this drop is occurring mostly in economically developed countries, the interesting news here is that where you have economically developed countries that use a lot of energy, that's the countries that are economically developed, they use a lot of energy, they have lower birth rates. And so in the developed nations, the birth rate's been dropping. In the underdeveloped nations, they continue to rise. And so it's pretty clear, the handwriting's on the wall, we need to get more nations economically developed, but to do that is going to require them to use more energy, but we cannot afford that to be fossil energy. So you can kind of see the picture here. The future has to focus on the development of new technologies in developing countries, and also we're of course the ones that are using the most energy, so we need to take care even more in this country to begin to reduce our dependence on fossil fuel. So this is kind of a global, carbon budget. You'll have to study this in more detail. By the way, I'm leaving you the notes, I'm leaving the PowerPoint, and the PowerPoint actually has notes on it. Hopefully you'll be able to do well on any of the questions from this part of the lecture. But we have an input in gigatons. A gigaton is 1 billion metric tons of carbon dioxide. To give you a feeling for that, Chesapeake Bay holds about 80 billion gigatons of water. So we're putting 36 billion tons of just carbon into the atmosphere through fossil fuel burning. We're putting about 3 in from land use change, where we convert forests to grow crops. Turns out that the oceans are taking up about 9 gigatons plus or minus a year. The land is taking up about 10 or so a year through photosynthesis. And the problem is the differential between what we're putting in and what the atmosphere is taking up is allowing the atmosphere to grow about 15, almost 16 billion gigatons of carbon a year is steadily accumulating in the atmosphere, and that's what's causing the increase in temperature. These are kind of the worst offenders. You see the dark colors, us, Asia, Europe not quite so much, in Canada. We share by any reckoning, we in China, the largest input of carbon into the atmosphere. And so it behooves us then to take the burden and begin to make the largest reductions in our carbon dioxide emissions. We, the United States, we, the developed world, we're the polluters. We need to take the first steps. Well, I've sort of outlined the problem, but how many of you have heard these statements made? Is the climate really changing? Well, maybe it's changing, but hasn't there always been a lot of variability? Remember those ice ages back there 20,000 years ago? Aren't natural forces much stronger than human ones? How about the sun and variability in the sun and other natural forces that we don't understand? How can humans be such a huge force? And I think the answer is because the Earth's climate is very sensitive to carbon dioxide and greenhouse gases. Then the argument is, well, why do we even bother to study this? Can we really tell what's going to happen? Our models are so uncertain. And even if we could, can we really do anything about it? Wouldn't it be just outrageously expensive to actually take this on? So, and wouldn't it just wreck the economy to do to these? Well, I think we've answered most of these questions. The scientific community, the technical community, and I think the answer is the climate is changing. Most people will not disagree with that. We now understand that humans are a force of nature because there's so many of us and we use so much energy. The climate models are getting better. We're spending a lot of money. You always hear the argument, well, you can't even predict the weather tomorrow. How can you predict the climate 100 years from now? Well, it turns out weather models and climate models are quite different. They're not the same models, but the weather models are getting better, as are the climate models. And yes, I'm going to talk about what we can do, and I'm going to argue that it won't wreck our economy. So just to give you a few statements from climate skeptics, we call them. Some people call them climate deniers, but perhaps a more objective term is climate skeptics. This is a statement from Lamar Smith, who represents the 21st District of Texas and happens to chair the House Committee on Science, Space, and Technology. Statement he made in January. The Obama administration wants Americans to believe that without government intervention, climate change will become a cataclysmic threat. Not true. That's not what the Obama administration says at all. Whether through exaggerated claims, worst-case scenarios, inflated projections, skewed statistics, or biased data, they want us to believe, they want to scare the public into funding our budget, a scientist, and so on, supporting costly regulations that would do very little to address global warming. So this isn't a political statement on my part. I'm just stating what has been cited in the newspaper. Let you draw your own conclusions. Earth science is not hard science, congressional Republicans declare. Senator Ted Cruz, you may have heard of him, the chair of the Science and Space Panel Commerce, asserted recently that Earth sciences is not hard science. We need to get back to the hard sciences, to manned space exploration. and to the innovation that has long been integral to NASA. In other words, he wants us to put our resources back toward doing space science, which we turned that from space science back to earth science in the 70s, and now the argument is we should go back to our original calling. So where do the presidential candidates stand? These are statements. Cruz, I said, is the head of the Senate subcommittee that oversees climate research, called Climate Change a Religion, voted no on a measure affirming that humans contribute to climate change. Kasich said of the climate change that he didn't want to overreact to it. And Trump, while the world is in turmoil and falling apart in so many different ways, our president's worried about global warming. What a ridiculous situation. He wants us to worry about potholes, which I think we should. The presidential candidates, Clinton is a strong backer of the space program. She's praised the economic benefits of lower carbon emissions while calling for smart regulations on fossil fuel. Sanders, in general, I do support increasing funding for NASA and will go even further in Clinton to call for a carbon tax. Now, a carbon tax really just makes it more expensive for folks to use carbon. The alternative to that is what's called carbon incentives, giving you an incentive based on the carbon you don't use. So here's an interesting sociological argument. Carbon tax tends to affect the poor because they're basically taxed for the carbon they use. So somebody in a lower socioeconomic class who depends on driving to work every day, perhaps for long miles, because, you know, to get a good job these days, you live in the cheap areas, you have to drive into the expensive areas, it affects them more. On the other hand, if you give carbon incentives for not using carbon, then you tend to shift the distribution from the upper end of the spectrum to the lower end of the spectrum. So there's some interesting arguments as to how to encourage us to use less carbon. This is an interesting one. At the Associated Press, they've told the reporters and the writers, you have to use the word, no longer can you use the word climate skeptics or deniers. Doubting or rejecting the science on climate change no longer makes someone a skeptic or a denier. In the view of a leading news organization, the Associated Press announced yesterday that it's instructing its journalists to use the word doubters, or those who reject mainstream climate science in their stories. So it wants to discourage the use of skeptics and deniers. Now I'm going to use this morning, as I said, plagiarize from the National Geographic's, who's done a marvelous job on reporting on climate science, but that organization has been recently bought by Rupert Murdoch. You may know him. So he basically is not a, shall we say, a liberal. And by 98-1, this is encouraging news, the Senate passed an amendment saying climate change is real and not a hoax. So we got that going for us. Okay, so back to the story. Climate change is here. I think most people agree that's here. And I think part of the answer is we need to understand what we need to do to mitigate climate change. We need to monitor it. And that's what NASA is doing by the number of satellites it has up. We make measurements of just about everything you could imagine that affects climate on the Earth. Aerosol optical depths, in other words, how hazy is the atmosphere. Carbon monoxide content in the atmosphere. You can see high concentrations where we burn forest in the tropical regions. Chlorophyll concentrations, clouds. This has a huge impact on climate. The clouds reflect, of course, light, and the more clouds we have, the cooler the Earth would be. The fewer clouds, the warmer it would be. So this is one of the big variables in understanding future climate. We monitor fire. We monitor land surface temperatures. We monitor the productivity of how much carbon dioxide is being taken up by vegetation, how much radiation we're receiving, what the sea surface temperature is, how much snow cover we have, rainfall, and so forth. So we treat the Earth as a patient, if you will, and I think a lot of people would like to see us not perhaps be so involved in doing that. But here's what we've learned. We've learned that temperature relative to 1960 and 61, the globally average combined land and surface ocean temperature has increased rapidly, or if you look at every 10-year averages, we see an increase of almost 6 to 8 tenths. We see observed changes in precipitation. As the atmosphere gets warmer, the water cycle accelerates. Evaporation, condensation in the atmosphere, precipitation from the clouds, that accelerates. And so we're seeing an increase in precipitation in some regions, not all, throughout. We're seeing an asymmetric temperature change. Here we see some regions are actually cooler, but where the big concern here is at high latitudes in the north, we're seeing very rapid increases in temperatures over the past few years. And this is a great concern because this is where much of the ice is stored. We're also seeing warming in the oceans, a slight increase in ocean temperatures. That's a concern because where the ice meets the ocean, this can undermine some of the ice caps. And as ice melts from the land, a particular interest here is the West Antarctic ice sheet. We can begin to see increases in sea level rise. This is the ocean warming data. I'm kind of speeding through this. You can look at it at your leisure. And we're seeing the Arctic summer sea ice extent decrease during the maximum period during the summer, which is about September. We see this, the minimum extent, we see that decreasing over time as the oceans begin to warm and raise the temperature of the ice above its melting. And we're also seeing changes in the snow cover. We're seeing a slight decrease in snow cover simply because the atmosphere is warming. It's not that precipitation is decreasing, it is that the temperature, the amount of snow is decreasing. So we see here the average sea level rise that we've been measuring for a while now. This is the rise per year. A global sea level rose by about somewhere around 0.2 of a meter in this time period. And this is essentially going to have some impacts that I will be addressing shortly. So, looking at the impacts on the Earth's ecosystems, the Earth ecosystem, the ice, the frozen part of the ecosystem, the atmosphere, the hydrosphere, the biosphere, we'll run through those shortly, quickly. So glaciers are retreating. This is a picture taken of the Muir Glacier. This is the Glacier National Park in Alaska. If you want to catch the glaciers, you might want to think about making a trip sooner than later. This is what the glacier looked like in '41 from handheld photography, what it looks like in 2004. The Muir Glacier, 1899 to 2003. And we see in Greenland, we're seeing the boundaries of the ice cap near the boundaries of the ocean, where it meets the ocean. These are decreasing very rapidly. The amount of ice stored on Greenland is declining very rapidly. And you can see the trends have increased, losing about 177 gigatons of ice a year. And a gigaton is about 1 billion tons. Chesapeake Bay has 80 gigatons. So you're losing a couple of Chesapeake Bay's worth of water every year from the Greenland ice sheets. And you can see this very vividly in this photograph from the National Geographic publication. We measure this from satellites. We can actually use lasers to measure the distance between the satellite and the sea surface. And as that sea levels rise, that distance decreases between the satellite and the sea level. And so what we see here is an increasing rise in the sea level as measured from NASA satellites from 1994 to 2006. Overall, a rise of a few millimeters per year. It's risen 4 centimeters, or about 1/10 of a foot in 10 years. So at this rate, it's rising about 1.3 feet per century, but we are seeing accelerated ocean warming and accelerated ice melting. This latest from the magazine Science, actually from Nature, but reported in Science. There are 2 major scientific publications, one in Britain, the UK, Nature, this one in our country, Science. Rising seas could displace more Americans than the Great Migration. A 1.8 meter sea level rise puts 13.1 million people at risk. That is people who live on the Pacific, near the Gulf, in coastal areas of the Gulf of Mexico, coastal areas of the Atlantic. 9/10 of a meter would put 4.2 million people located near the coast at risk. And this means actually losing real estate or having to mitigate by building seawalls. This is what Florida would look like. This is from National Geographic's with 5 feet of sea level rise. You can see here the Keys. You can see what was once the Everglades. So Florida retreats from where it is now with 5 feet of sea level rise to where dry land would be. A lot of this real estate, of course, would be inundated. Here you see Fort Lauderdale, Miami. So this is exactly the kind of impact, the first kind of displacements we're going to see from rising sea levels. And we think that those are going to accelerate even more quickly. This is 6 man-made islands in Florida, 6 man-made Venetian islands. The Venetian Causeway here connects Miami Beach to Miami in the distance by way of 6 man-made Venetian islands. And it won't take much sea level rise to begin to cause displacements there. But while our country is being threatened, we see this, again, this is from National Geographic. A photographer traveled around the world to document the impacts of sea level rise. And we can see this happening everywhere in different parts of the world. And we also see an increase, this is the storm intensity. This is the number of storms, of intense storms. You have to understand what the definition of an intense storm is, but it's defined in the notes. And what we see is a slow rise, very rapid rise since about 1980 in the number of intense either flood events, hurricanes, typhoons. Those are all intense, severe storms, I should call them. And then this is what Bangladesh would experience. This is the number of meters above sea level. So we're going to see very large impacts from that and very large displacements in the population. This again from National Geographic, the cost to various areas due to sea level rise, all mapped out here. Losses in 2050 of an extreme weather event, overwhelmed sea level rise, defenses. So it's not only the average sea level rise that's important, it's the storm surge that occurs. I don't know if you remember, or even living in Baltimore a few years ago, we had a storm surge come up the Chesapeake Bay, and where the convention center is now was about knee deep in water. I think the average sea level, the ocean rose 7 feet. If you go to the inner harbor right now and stand by the Constitution, where the brickwork is around the Constitution, you're looking at the Constitution over there, the brickwork at high tide is now underwater. And I don't know when that was put in the, I guess, 80s, 70s, somewhere. So we're already seeing sea level rise affecting. So we're going to see, as the first impacts, sea level rise. Ice is rapidly vanishing. This is displacing a lot of inhabitants in the north. A lot of these villages are connected by ice in the wintertime, where they can use their sleds or skidoos to go across the ice. This is beginning to disappear in the wintertime in some places. It's affecting their hunting. Here's a guy hunting for polar bears with his lying on the ice, shielded by his little shield here. Hunting, that's being affected because polar bears are being affected by this. Perhaps the first large-scale victim of sea level rise will be the nation of Kiribati, located on the Gilbert Island chain in the South Pacific. This is the island here, located in the South Pacific. And this is a picture of the island. You kind of see that they have a lot of their aquatic farms where they raise their food. They're just above sea level in this tiny little nation, and they're already beginning to experience, this is again for the National Geographics, beginning to be affected by sea level rise in their part of the world. We look at the effects on the hydrosphere. What's happening in the hydrosphere as the oceans absorb carbon dioxide, they're essentially becoming more acidic, like maybe a form of Coca-Cola. And as they become more acidic, it becomes much more difficult for shell-bearing animals to form shells, because the dissolved carbon dioxide in the water creates carbonic acid. The carbonic acid then breaks down the bicarbonate and hydrogen ions, and the hydrogen ions then react with carbonates in coral and shellfish, and that begins to harm shell growth reproduction. So this has been one of the big absorbers of CO2. As the atmospheric carbon dioxide has increased, it's increased the CO2 concentrations here, and that's creating more acidic ocean. Now, shamefully, I bought a plastic water bottle with me from the cafeteria. This is what eventually happens to these water bottles, a lot of them. They wind up in the great plastic garbage patch in these gyres in the middle of the Pacific Ocean. Here's Canada and the US and Japan. You see these large circulating wind currents kind of collect all the garbage. And this is a plastic garbage patch about the size of Connecticut. And if you see what it looks like, this is sort of the big picture. What happens eventually, though, is these plastics begin to break down into tiny, tiny pieces. Those begin to be ingested by shellfish and so forth. So be sure you recycle your water bottles and your plastic garbage bags. Permafrost is another issue. The northern part of the globe. This is a picture of where the ground is permanently frozen, this purple region. This is beginning to warm. I showed you the picture of how warm this area is getting. This is beginning to thaw the permafrost. The permafrost contains a lot of organic materials that have been stored there since the last ice age. As those organic materials begin to thaw, the bacteria in the permafrost begin to metabolize the organic materials, and they create, in addition, more carbon dioxide and methane. So there's about as much carbon stored in the permafrost as actually more than there is already in the atmosphere. So there is a concern as to what the effect of a warming Arctic will have. This is a picture of what the permafrost can look like. And enough carbon is stored in the global Arctic permafrost to increase the atmospheric concentration over what it is now by somewhere between 60 and 188 parts per million, we don't really understand this problem very well. Fire is another issue. A lot of burning to clear crops for forest in both Africa and South America. So fire frequencies have increased. We've monitored these in NASA. We can see they've leveled off a little bit as there have been some mitigation measures on the part of the United Nations to try to preserve some of this forest land. I love this picture from National Geographic's people inspecting their wind farm on these electric scooters. Okay. What we need to do is to hold the global temperature change to less than 2 degrees centigrade from where it was in the pre-industrial revolution. And this is based on a number of analyses that show what happens to various ecosystems as the temperatures were to rise above 2 degrees centigrade. We're at about this point somewhere already. We can see this Arctic summer sea ice is, we've seen the evidence of thaw there. We've seen the evidence the Greenland ice sheet is already beginning to thaw. And so we have drawn a line from studying these various ecosystems at 2 degrees centigrade to try to keep our emissions below what would be required to hold a 2 centigrade level. So should I be wrapping this up?
What we can do, I know the students do have a few questions that they had.
Okay.
Brought them to my attention in our last lecture.
All right.
So I figured the last 10, 15 minutes we could spend with students.
Okay, let me just say quickly, there are many things we can do about this. Let me skip out of this. And let's go to all the stuff we can do, because that's the good news. Find this. Here we go. These are the steps that a number of analyses have shown could actually reduce the level of emissions so that our global average temperatures do not rise above 2 centigrade. We can improve our agriculture and forestry by making this more efficient, reducing the amount of fossil fuel used. We can certainly improve reduce our emissions from using alternative energy sources, solar, wind, driving cars more efficiently. We can begin to capture some of the carbon dioxide out of existing fossil fuel plants. We can become much more efficient in our power generation. And of course, we can become much more energy efficient and through conservation practices, reduce our emissions. So the good news is that we have the technology to do this. The bad news is that we're sort of in we're not reducing this as quickly as we could because there's a lot of resistance to doing that from many of the industries that actually depend on using carbon-intensive fuels to make their profits. So we need to convince them that the way of the future is to go toward non-fossil fuel sources, that they can get rich doing that as well as they can get rich selling coal and oil and begin to reduce the carbon dioxide emissions. And I think most of the science community is very optimistic that this can happen. But it's going to be up to you guys more than our generation to do that. So with that, I will On that hopeful, optimistic note, I will open it up to questions for anybody who has questions. Yes?
You have up here agriculture, and obviously a big contributor to emissions is the use of fossil fuels in machinery
Right.
and transport with agriculture. But there's also methane that comes from livestock themselves. Would, to mitigate that, would it require a change in human diet, or do you think that there's some other way of accounting for that?
Well, let me just show you one brief view graph to show you the answer, or show you an answer. It's called, what's the beef? So this is from the National Geographic magazine again. Favorite food of Texans is beef. This is the average square footage required to produce 1,000 calories consumed by humans in the US. This is beef. This is dairy, pork, poultry, eggs. Average feed in thousands of calories to produce 1,000 calories consumed by the US. So you can see that meat, mostly beef, is the one that's really calorie intensive in order to raise beef for us to eat. So the message is simple: don't eat much beef. In fact, becoming vegetarian might be a good way to go, but at least becoming a vegan. I like to stick to poultry myself and eggs, and I think that is certainly a good way to maintain your health and reduce the consequences of agricultural emissions. Eventually, it'd be great to have combines that run on solar or something like that. Nuclear combine. That's a scary thought. I don't think so. Any other questions? Yes.
Now, I don't know too much about it, but I heard there's a hole in the ozone.
Yes.
Is there any way that we can compare that, or what are the ramifications of that? Is there anything we can do to?
It's being exacerbated by climate change, but in the 80s, we actually had the Montreal Protocol. A bunch of governments got together and says, we got to do something about this ozone hole. And what they did was outlaw the use of chlorofluorocarbons, which is what we use in our air conditioners to, cool the thing. And the chlorine in the chlorofluorocarbons, when it gets emitted into the atmosphere, it then destroys the ozone. O3 becomes oxidized, and that created the ozone hole. So we actually, the Montreal Protocol reduced the dependence on chlorofluorocarbons. Now when you go to get your automobile air conditioner charged, you can no longer do it with Freon. And so that's the hopeful news. Now unfortunately, climate change is destroying some of that progress, but hopefully when we get climate change under control, we'll get the ozone hole smaller. And that's important because ozone blocks out harmful ultraviolet radiation from the sun. Ultraviolet radiation is very intense, high energy. It disrupts the DNA within our skin. It can cause skin cancer, but it can also have devastating effects on some microorganisms. So it's important to get the ozone hole patched, fixed. Anybody else? Hunger overcomes intellectual curiosity.
I have a question.
Yeah.
So way back in the beginning, you mentioned that the Earth's solar budget hasn't varied much over the past 20,000 years. How do we know that?
From measuring it?
How do we measure that?
Well, and recently we measured from satellites. In the past, we can look at energy balance and determine that the energy balance wasn't much different than it is today from models. You can't measure it, obviously, you can only infer it. But we know, physicists know a lot about the physics of the sun, and they know that the sun is a fairly stable system, except for the sunspot cycles, which are 11-year cycle, and that does cause tiny changes in the solar. But so there's a lot of reasons to believe that's not the problem. especially in the last 30, 40 years. So we have measured it with so many different satellites. It's just a very stable number, and it's not. The increases in the solar radiation aren't nearly enough to cause the change in temperature that we're seeing. So, but you know, people like to throw that one out. How do you know that? So it's a good question. I think we know it pretty well. Somebody else?
When comparing the rate of human-caused temperature increase in the modern era to the temperature increase caused by caused by the Siberian traps basically being ignited by volcanic eruptions back in the Permian, it looks like we're actually, at the moment, increasing climate change on a faster rate than the climate change that caused Great Permian die-off, where microorganisms actually went extinct, where we can see them in the fossil record, which is terrifying, really, because there's a reason it's called the Great Permian die-off, and it's not because things were happening.
Yeah, there are a lot of signals like that that are causing us great concern. The fact that the radiation budget only differed by a fraction of a watt per meter squared from the last ice age. And again, we should of course be concerned about catastrophic climate change. But I think the thing that's going to make us really unhappy in the near term is to see our climate changing so radically, experiencing the displacement from that. But yeah, we need to worry about that, of course. And because the climate system has been stable for thousands of years, that's the good news. We probably won't destroy the Earth. We may just destroy us.
Life will find a way. I mean,
Life will find a way,
it
right?
survived just about everything that's happened.
Right, except us. No.
Yeah, we're doomed. We're doomed.
Are there any other questions that you'd like to ask of Dr. Forrest at this time?
Well, thank you guys for being attentive.
I'm
and,
sure we'll stay around
Yeah, that's it.
for a minute or two if you have any questions.